Good afternoon, everyone. Good afternoon, everyone. I welcome you all to the last session, the problem solving or the live interaction session for the NPTEL course Fluidization Engineering. So, the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. While this live session is handled by myself, Ankar Kartiga, a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, this is the last session for this. Once, just a minute. So this is the last session for this particular course, wherein we discuss the important points that we covered throughout the course and also some important sample problems that we will visit once again and have an explanation so that it would be helpful for you guys when you appear for the exam or whatever the thing is. So this is just a recap of whatever the things that we saw throughout the course and what are all the important points that we covered during the course. So I am very grateful for those people who attended the course, and we'll see this session, and at the end we can have feedbacks if anyone is willing to provide, or else yeah. So uh, yesterday was our last session for the course. In yesterday's class, we saw about the fluidized beds, heat transfer properties, and the design of fluidized beds. So, I hope the problems in yesterday's class were clear enough for you guys. So, we'll move on to today's problem. Yeah. So, just a quick recap of whatever the things we saw in the course. So, in week 1 to 2, we saw what is introduction to the phenomenon of fluidization with emphasis on advantages and disadvantages of fluidized beds and industrial applications of fluidized beds. And week 3, we saw about the characteristics of solids, classification of solids, flow characteristics, and its outline in different types of fluidization. Week 4 to 5, it was about flow pattern of fluidization system, flow pattern transition, flow pattern map, frictional pressure drop, and its model to analyze, solid movement, mixing, segregation, and staging. And week 6, it was about gas distribution system, types of gas distributor in small and large scale industries, design of distributors. And week 7, it was about bubbling fluidized beds and with gas dispersion and gas interchange in bubbling beds, mixing characteristics. And week 8, it was about entrainment and elucidation from fluidized beds. And week 9, it was a study about attrition and attrition mechanism and its analysis by model. And week 10 to 11, it was about mass transfer phenomena and particle to gas mass transfer or its analysis by model in 2 and 3 phase system and modeling. And week 12, it was about heat transfer phenomena, heat transfer between fluidized beds and surfaces, and modeling, design of fluidized bed reactors, and design for physical operation in catalytic and non-catalytic systems. So all these things we have covered till yesterday's class. So the books and references for the courses, first one is Cooney and Levenspil's Fluidization Engineering. As we have seen, this almost covers the all the concepts required for the course. And second one is D. Gidaspo's multiphase flow and fluidization, continuum and kinetic theory description. So as we discussed before, fluidized beds can be modeled in two ways. In wherein we model the fluid as a continuum, but for solids we have two properties, either as a continuum or as a Lagrangian. So or as in discrete particles. In the continuum theory description, what we do is we average the solid properties by imposing a theory similar to that of the kinetic theory of gases. So we call it a kinetic theory of granular flow and use it to assume the assume the solids behaving like a continuum description. So this book basically covers all the aspects regarding to that description of solid medium. Based on the kinetic theory, we call it kinetic theory of granular flow or KKTGF. So And third one is LG Giblaro's Fluidization Dynamics. And fourth is SK Majumder's Hydrodynamics and Transport Processes of Inverse Bubbly Flows. So now we'll start with the uh, class. So basically, what is fluidized beds? So fluidized beds are nothing but wherein we pass the fluid, which can be gas or liquid, inside the packed bed, so that we are giving it to behave like a fluid medium or the continuum. So when we pass the fluid inside the bed at a sufficiently higher amount of velocity, the bed starts to behave like a fluid. The particle starts moving, and because of that the packed bed gets transformed into a fluidized bed. So this particular thing is called as fluidized beds. So initially the particles will be compactly packed inside the bed. After it the velocity is crossing the minimum fluidization velocity, the particle starts to move, and we have a voidage would be increasing in that case. So in general, in packed bed, the drag force exerted by the fluid on the particle is very less compared to the gravitational force. Thereby, the particles would not be moving in the bed. Whereas once the velocity has exceeded the minimum fluidization velocity, the drag force on the particle would be exceeding the gravitational force. Thereby, the particles also would start moving. So this is known as fluidized bed. So why do we prefer, before that, what is minimum fluidization velocity? We have seen more we have told about minimum fluidization velocity. So what exactly is minimum fluidization velocity? So what happens is that this is a graph explaining what is fixed bed and what is fluidized bed, and how we can analyze it, or how we can identify it. So this is a graph between pressure drop in the y-axis and air velocity in the x-axis. So as we can see that initially when we are increasing the air velocity inside the bed, till a particular point the pressure drop keeps increasing. So this is known as fixed bed. Once a point will be reached where beyond that point, how much ever we increase the velocity, the bed would the pressure drop would not be increasing. So after that point, it is known as fluidized bed. So before that point, it is known as fixed bed. So the point at which this transition happens is known as minimum fluidization velocity. We call it as UMF. So before UMF, the bed is fixed bed. After UMF, the bed is fluidized bed. So this is the case, and this would be further beyond the fluidized bed. We have so many regimes of fluidization which should be varying with the amount of air velocity that we are using, that we are passing inside the bed. So why do we prefer fluidized beds? So basically, what are the advantages when we are dealing with the fluidized bed is, the first one is it is applicable for large or small scale operations. It can be used for large scale operations also, which may not be possible with some other reactors or so. And since we are, as we have seen in the first slide, because of the movement of solids, we have so much voidage, and the chances of the particles to have more reaction with the velocity would be increased because of the increased surface area. The surface area would be increased in the fluidized bed compared to the packed bed. The surface which is coming in contact with the fluid. So it enhances the heat transfer and the mass transfer rates. And because of that, it is preferable to use fluidized beds. And the third one is uniform temperature gradients. For example, if we are using packed beds, there are chances for hotspot formation inside the beds. So in such cases, when we need to avoid it, we can go with the fluidized beds, because it enhances uniform mixing of the particles. The chances of the temperature gradients inside the bed would be around 2, maximum would be 2 degrees Celsius, which is always feasible. But in packed beds, chances of the hotspot formation, where at a certain point the temperature to be increased very high, is always there. So in such cases, it is advised to go with the fluidized beds. And if we think only there are advantages and there are no disadvantages, it is not the case, because again we have a few disadvantages when we are dealing with the fluidized beds. For example, in bubbling, actually there this we would be seeing in further slides. There we one at I mean we would have known by this time because of attending the lectures throughout. There is a one particular regime called as a bubbling regime, where which we can observe the bubble formation inside the fluidized bed. So when we are dealing with the bubbling fluidized beds, it becomes difficult to control the bubble formation. So understanding the complete dynamics of the bubbling beds is essential to control the bubble formation inside the fluidized beds. So it is one disadvantage. And the second one is particle erosion takes place and lead to loss of solids. So in fluidized beds, since the particles also starts to move, the particle-particle interaction would be very much, and because of that, the particle may collide with the other particles and all walls. So it leads to the corrosion, I mean erosion of the particles, wherein the particles loss would be there. It in such cases, it is like if we are using costly materials as a solid, it is not advisable to go with the fluidized bits, because the particles loss would be there, which is if the catalyst in reactions are very costly, it is not advisable to use the fluidized bits. And third is pumping cost might be very high. So since we are passing the fluid inside the bed, we depending on the pressure drop of the beds, the pumping cost would be varying. So the proper design of the fluidized bed is essential. Otherwise, the pressure drop would be very high inside the bed and thereby leading to higher pumping costs. So therefore, it should also be taken into account when we are designing the fluidized bed. But in general, that is one disadvantages. So, and where do we use fluidized beds? So in chemical engineering industries, if we look, there are so many industries where we can find the use of fluidized beds. For example, reactions like Fischer-Tropsch synthesis and polyethylene manufacturing, and there are so many polymerization reactions and nuclear fuel preparation and chemicals like aluminum anhydride production. Everything involves fluidized beds. And also if we see the fluid catalytic cracking, which is commonly used in oil industries, I mean commonly seen in oil industries, employs the fluidized beds. And also it's like processes operations like drying, adsorption, cooling, everything can also be done by using the fluidized beds. So the only thing that needs to be looked into while going with the fluidized bed is that the particle properties like particle density, particle uh, shape, size distribution, and their velocity, and properties like geometric, physical, everything needs to be accounted properly, so that it would be giving us advantages which would help us overcome the disadvantages when dealing with the fluidized beds. So what are the regimes of fluidization? So this one, as we have seen in the before slide, when we are passing the gas or the liquid inside the fluidized bed at a very low velocity, the bed would not, the particles would not be moving, so that they are packed, as similar to how it would look when we are I mean it is like a packed bed. The particles are not moving, and so they are closely packed. This length is, let us keep it as Lm. So here the fluid velocity is very low, so this is known as fixed bed. So after that, if the velocity is increased, actually this is with increasing velocity, the from left to right we are increasing the velocity and observing the behavior of the bed. And the second case, we are increasing this velocity by a slight fraction, and the bed is not exactly closely packed, but rather they are loosely packed, but they are not moving anywhere. So this particular regime is known as minimum fluidization. At this point, the weight of the particles is counterbalanced by the drag on the particles, which is exerted by the fluid. The fluid exerts a drag on the particle, which is counterbalanced by the weight. I mean, which is so the weight is equal to that. So this point is known as minimum fluidization or incipient fluidization. So after this, there are two types of thing we can observe depending on whether the fluid we are using is a liquid or a solid or a gas. So if we are using liquid, what we can observe is that the particle starts to move and there is a very uniform fluidization. So it is known as smooth fluidization or homogeneous fluidization or particulate fluidization. So in this particular thing, when we are using liquid, the fluidization is smooth. There is no bubble formation. So it is called as smooth fluidization or homogeneous or particulate fluidization. So this is with increased velocity after UMF. So the velocity here is higher than UMF. But this is the case when we are using liquid. But what if we use gas as an inlet fluid? So if we use gas, we are passing the gas at a higher velocity than the UMF. So at this point, the bubble starts to form in the fluidized bed because this is where we are dealing with the gas. So bubble formation, as you can all see, starts taking place. So this is known as bubbling regime. So with further increase in the velocity, it can be observed that the bubbles grow in size. So the bubble starts forming at a very small size and they keeps on growing in size. And this is known as axial slux because the bubbles growing in the axial direction. Like from here to there, the bubbles are growing. And there comes a point with increase in velocity where it can be observed that the bubbles almost, what happens here, they are almost reaching the diameter of the column or the vessel. So this is known as flat slugs. So this is axial slugs and this is flat slugs. So the bubbles starts growing in size, and after a point what happens is that the bubbles on reaching the surface, they starts to break up. That happens over here. But if we further increase the velocity, there is bubbles are starting to burst out and the solids they are carrying are thrown away. So because of that, it can be observed a turbulent regime inside the fluidized bed is observed, wherein a very vigorous motion of fluid is taking place, and because of that the solids are also getting very well mixed. And after a point what happens, the solids would be escaping from the bed, where the phenomenon observed is known as pneumatic transport, where the solid fraction becomes very less. So in such cases, what needs to be done is we need to keep a recirculator so we can collect the escaping solids and recycle it back inside the bed. So it would be like at a certain height we would be having a recirculation cycle where we would take the solids escaping from this and pass it back into the system. So these are all the fluidization regimes that is commonly observed in the fluidized beds depending on the velocity at which we are passing the fluid. So all this, the major influencing factor here is the fluid velocity. So that is the fluidization regimes. So if we ask whether all solids behave the same inside the fluidized bed, that is not the case. For example, the particles would be varying in what aspects? They would be varying with respect to density and the size of the particles. So, since not all solids are behaving the same inside the fluidized beds, GELDAT classify the solids into 4 categories: A, B, C and D. So this is the plot showing that. So here in y-axis we have the density difference, that is rho p minus rho f, which is the density of the solid minus the density of the fluid, and at the bottom we have the diameter of the particle dp. In x-axis we have the diameter of the particle, in y-axis we have the density difference between the solid and the fluid. So at very smaller particles comes under the class of GELDAT C. Since these particles are very small, considered like powders, so they would be very much cohesive in nature, right? They would be sticking to each other. So it is very difficult to fluidize these particles. Like GELDAT C particles are very difficult to be fluidized. Next comes the GELDAT A particles. So where in GELDAT A particles we have the diameter of the particles are higher than the GELDAT C particles, but still they are lower than GELDAT B and GELDAT D particles. So what is the advantage? Here actually in industries, if we look, majority of the industries would be using gel dot A particles, because in gel dot A particles it is difficult to I mean not difficult, it is bubble formation is very much minimized in the gel dot A particles. And also like A dash, as you can see, is that the fluid catalytic cracking FCC catalyst comes under gel dot A class. So it is the A dash is the FCC catalyst. So these particles are very easier to fluidize, which is given by aeratable. So but bubble formation is again minimized here, but it is very difficult to model the fluidization of gel dot A particles, because imagine the particle hydrodynamics to study that, the particles will be very smaller in size, like 100 micrometer and all would be very small. So in order to study them, it is very difficult. I mean comparatively it is better than gel dot C, but again study of them is quite tricky. Next comes the gel dot B particles or the sand like particles. In gel dot B particles, it very much, we see majority of the literature studies on fluidized bed would be involving around A or B, and B is very much used in fluidized beds. For example, the sand like behavior, like they are having diameter higher than the gel dot A particles, and it is very easier to fluidize, but the thing is the bubble formation is very much observed in gel dot B particles. So it is, if we understand the bubble dynamics well, it can be used, but then bubble formation, it sometimes it poses difficulty when we are dealing with certain types of processes. So it is a but it can be easily studied by when we are dealing with the fluidization of gel dot B particles. Next comes the gel dot D particles. These particles are very small, larger in size. For example, like above 1000 micrometers in size. So it is like the bubble formation in these type of beds would be very vigorous, like large bubbles would be formed. So therefore the beds that is used would be, I mean the particles that are used would be in gel dot D particles, sorry, in spouted beds. For in spouted beds actually, we pass the fluid inside the bed height would be limited. So the velocity would be fluid would be passing in the center, and the particles would be thrown away. Like if this is the bed, the fluid would be passing here, and the particles would be falling down in the annular region if we consider this region occupied by the fluid. So in this region and this region, the particles will be falling down. Because of that, the particle motion would be taking place in the gel dot spouted beds. So gel dot D particles are mostly used in spouted beds because they are very large in size. It is difficult to control the fluidization of the gel dot D particles. So okay, so next comes the gas distributor considerations. So if when we are considering the design aspects of fluidization, the main thing to be considered is gas distributor. So we have various types of distributors like porous, perforated distributors and all. So what distributors would we be going with, and why do we need to go with the specific distributors? So the main thing to be considered is pressure drop or the pumping power requirements. So in fluidized beds, the main thing is because of the distributor, there would be additional pressure drop. So if we are not accounting it properly by giving a proper design of the distributors, the pressure drop would be very high, which should be influencing the pumping power cost. So if the pressure drop is very high, the pumping power cost also would be very high. So in order it would not be efficient to run the industrial fluidized beds with such higher costs. So it is very much required to take into consideration the pressure drop aspect when we are dealing with the fluidized beds gas distributor design. And also the another aspect is that when we are dealing with the gas distributors, the construction strength, okay, the construction strength of the materials needs to be accounted. So only on account taking into account the construction strength of the materials, it would be effective to study, because unless we know the how what material it is made up of, it needs to withstand the velocity of the fluid at such high velocities. So construction strength needs to be accounted when we are designing the gas distributors. And next is the cost for some materials, because we are dealing with some materials may be easier to be used uh, when considering all other aspects, but the cost of the material would be high, so it also is an influencing factor. And resistivity against thermal stresses, because in fluidized beds some reactions would be happening which would be giving out reactions, sorry, which would be giving out heat. So heat transfer would also be taking place inside the bed. So resistivity against thermal stresses is an important factor to be considered when designing the gas distributor. And the fine like the pore, there would be different types of distributors. So there are chances of the openings or the uh, by the particles, that is the finer particles might be clogging the distributor openings, or the particles would be getting eroded and they would come back and clog the distributors. So it needs to be accounted when we are dealing with the distributors. So we'll just see what are all the different types of distributors. So the first we have the perforated or multi-orifice plates. So this is like sandwiching perforated plates. So we have two metal opening. I mean, we can see there is this, we have two metal plates, and in between we have sandwich straight. So this is normally used, and this one is a staggered perforated plates. Here we can see that two lines are not exactly aligned, and we have this is known as staggered perforated plates. And this is dished perforated plate, where we have a curved plate distributor, and this is the great bars, and this all comes under the perforated or multi orifice plates. So the another one would be we have a single orifice opening inside the fluidized bed, which would be mostly used in understanding the bubble formation that is taking place inside the beds. So in CFD studies, if we are to study the bubble formation inside the in the fluidized beds, single orifice opening would be used. And next is the tuyers and caps. So this is the porous plate tuyers and nozzle type and bubble cap type, and this is a slit nozzle type. So the particles would be the fluid would be passed through this, and the major advantage is that the backfall or the particles falling back would be prevented when we are using these type of distributors. And this is a pipe grits and spargers. So grit and spargers would be used to pass the fluid inside the bed. So this is one type of design. And next comes the bubble behavior for different types of gas distributors. So when we are passing the fluid inside the bed, it is not always same type of bubbles will be formed, right? So in bubbling bed, it is necessary to study what are the how the bubble formation is happening. For example, if we look into this picture, we can see this is the porous plate distributor. So depending on the type of distributors, the bubble formation size and shape is getting influenced. So in porous plate distributors, initially smaller bubbles are getting formed, and as they grow, as they go up, due to bubble coalescence, they grow in size, and once on reaching the surface of the packed bed, they again burst out and drop back the solids. So this is what happens in the porous plate distributor. And next is the perforated plate distributor. In perforated plate distributor, we have the perforations through which the fluid passes. So initially, depending on the opening, that is this nozzle opening, the fluid and this nozzle opening and the fluid velocity at which it is passed, as you can see, the bubble has grown this much in size. So this is known as jet penetration length. So depending on the opening and the gas velocity, the bubble length, that is the bubble height, would be influenced. So once these bubbles are forming, and after a certain length, that is till this length, after which the bubble gets dispersed from this opening and they move on their own. This is what happens when we are dealing with the perforated plate distributors. And option C, it is nozzle type tuyers, and this is bubble cap tuyers. In both the cases, once the fluid is passing through this, here the bubbles are getting dispersed from the opening, and after that they grow in size near the walls of the column. So this is similar in the nozzle type and the bubble cap tuyers. So the bubble size and the bubble shape is highly influenced by the gas distributor design. So when we are designing the gas distributors, it is very much essential to consider all these things also. So it would be beneficial when we operate in the fluidized beds operation. So solids movement in bubbling fluidized beds. So this is what bubble formation also in turn affects the fluidized beds. So for example, this is the different types of fluidized beds based on the geometrical design. So in this, it can be seen that the this is actually the length and the if depth. Sorry, the if we keep this depth and this is the length, they both are similar. So like a square shape. So in this case, if the velocity is very low, the solids would be going up near the walls of the column and they would fall back in the center. This is what happens when we are dealing with the bed dimensions are similar in the length and the depth, or the diameter and the depth, whatever, and the velocity is very low. If the velocity is very high, we can see this regime where the solid starts moving from the center and they drop out near the walls. This would be the most commonly observed phenomenon happening, wherein the solids would be rising in the center and falling back near the walls. So this is what happens. But in case if the depth, that is this height of the bed, is very higher than this dimension, the different types of solid behavior is observed, wherein the particles go from here to the center and after that they fall back in the center, from the center, and the additional movement is observed near the surface of the bed. So if the depth of the bed is very small, what would be happening? The particle recirculation is happening in some specific zones itself. So for example, it can be seen that the particles are going up here and falling back here. Similar thing would be observed, like they go up and fall back. So if the distributor is uniform, this is the case. Whereas if it is tuer type distributor like this, it can be seen that the particles rising in the center and they fall back, and this type of circulation happens in the gap between the distributors, and on top of the distributor, that is the openings, the particles are traveling up. So this is the general fluidized bed pattern with the very high depth and compared to this dimension. So here this is similar to that, where the particles are going from here to there. Like general fluidized bed would be, particles would be going from the center to the top. From the center it would be traveling upwards, and near the walls it would be falling downwards, and some recirculation would be happening elsewhere. So depending on the bubble movements, the solid solid pattern is highly influenced. So it is very much essential to understand what is happening inside the bubbling beds, so that we can understand the solids solids moving pattern. So one more thing is, if we are dealing with a single particle inside the bed, that is a different story. But when we are dealing with more than one particles which are differing in terms of their density and the size, so the particles can either segregate or they can be having complete mixing. So it is very much essential to identify which regime it is following, like it is mixing or happening or segregation happening. That can be influenced by identifying the velocity that is passing inside the bed. So generally what influences these would be the particle properties, like if we consider two particles are there, like coal and quartz, we need to know the we know the density of these particles which would be differing, and then we need to know whether the size of the particles are the same, or whether the size of coal and quartz are remaining the same or they are differing, or and also we need to know whether they are of the same shape and all, and mixture composition. For example, how much of coal is present inside the system and how much of quartz is present inside the system, and the fluidized bed height and superficial gas velocity. Obviously the gas velocity would be influencing whether mixing is happening or segregation is happening. For example, this is a bubbling bed with the binary mixture. So depending on the gas flow, everything would be can be identified. So the major objectives in most cases would be to achieve good mixing, and based on the density adjustment. And one example would be coal beneficiation, where so many particles would be used. So on all those things, it becomes necessary to identify mixing behavior or segregation behavior. And for that we have, if the particle density is low comparatively, we call them flotsam particles, and if it is very high we call them as jetsam particles. So if based on that, the particles may either go to the top of the bed or they would be settling inside the at the bottom of the bed. So uh, based on these, we can have completely mixed bed, perfectly mixed bed, or completely segregated bed, or partially segregated bed, and everything would be depending on these only. Like we have a quantity to quantify this, known as segregation index or mixing index, wherein we define the segregation index as mass fraction of the flotsam particles on the top of the bed to the mass fraction of the flotsam particles in the perfectly mixed bed. So based on that, we define the segregation index. So that needs to be analyzed before dealing with the fluidized beds, when we are dealing with more than one particles inside the bed. I mean, obviously, if we are looking at the industrial processes, there are in no way we use only single particles. Single particles would be used only in the laboratory study. In all other cases, in industry, whatever process we are taking, we can not say the size would be the same in most cases. And if in most applications where we are dealing it, the size and the density also would be differing. So studying of the solids mixing and segregation is an important one. And next is the entrainment and the elutriation inside the bed. So in the last regime of the fluidized beds, we saw that once the particles fluid velocity is very high, the particles would be carried over from the top and pushed back inside the bed. So there is a regime up till which the particles will be moving only till certain height. So after that, mostly the particles would not be escaping into it. So this particular height is known as like the bed should be designed such a way the particles would not be escaping. So for that particular design, we need to identify that bed height. So basically, what is entrainment is that entrainment is the carryover of the solid particles from the dense bed medium to the top portion. So the chances of the finer particles getting escaped is very high, and also the elutriation is nothing but if the finer particles, we are collecting the finer particles in a specific size range, we call it as elutriation. So for example, if this is the fluidized bed, we are passing the fluid inside the at the bottom of the bed. So we have a dense phase bed wherein we can observe the bubble formation and all. So after that, till this particular height, this is known as transport disengaging height. So the particles weight fraction would be reducing at these levels, so they would not be remaining constant. So this is known as transport disengaging height. So after this zone, we call it lean phase or a freeboard height, so till the top. So in order to design the fluidized bed perfectly, it becomes necessary that we understand all these things. So we cannot allow the particles to escape escape from the fluidized bed design. And after this regime, the particles would be there whose free fall velocity is very much less than the gas velocity. So their chances of these particles getting escaped is high. And as we can see that it is bubbling regime, and splash zone is nothing but where we can see both the bubbles formation, and I mean the dense bed and the lean bed. Here, okay, sorry, here the particle fraction would be constant, not varying. Only here it would be that varying. And for modeling of these beds, we have the particles to be one set of particles would be moving up, and after that they would be falling down. So these are the terms like agglomerates and fine particles which were used in Cooney's, I think it is bubble coalescence model or something. So these terms were used. So it is a part of understanding how the solids weight fraction would be varying, and how the solids would be carried over if it is a reaction, or if it is a process involving the solids carryover. It becomes necessary that we allow the recirculation to take place, so that we are not losing the valuable materials. And next is the attrition in fluidized beds. So when particles are moving against each other, there would be a lot of friction between the particles. So because of that, it becomes necessary that we understand what is happening inside the bed, so that if the larger particles are getting eroded, they would be reduced in size, and those finer particles would be lost in the during the process. So for example, the attrition in fluidized beds can be observed by two aspects. The first one is it can be abrasion or it can be fragmentation. In abrasion, what happens is that because of the particle-particle interaction or the particle-fluid interaction, the particles would be there, and some amount of fines would be getting escaped from the particles, like they would be getting eroded from the particles. Or in fragmentation, because of the forced contact between the particles, these particles would be broken down. So this is first one is known as abrasion, this is known as fragmentation. So there are various models to study these attrition in the fluidized beds. So all these we studied in the last classes itself. So next, the important thing when we are dealing with the fluidized bed is the mass and heat transfer phenomena happening inside the fluidized bed. So for a what is the main purpose of studying fluidized beds? Because we would be using it for reactions or something. So it becomes necessary that we understand the thing happening inside the fluidized beds in terms of the mass transfer and heat transfer phenomena. Because already we saw how we prefer the fluidized beds when we are because in packed beds the chance hotspot formation and all would be there, and in fluidized beds it is evenly distributed. The temperature will be evenly distributed. So so the first thing is mass transfer in fluidized beds. So it can be considered in three types. Like mass transfer in fluidized beds can be studied by using three mechanisms. The first one would be diffusion, the second one is convection, and third one is chemical reaction. So when does mass transfer in fluidized beds takes place? That happens by means of three factors. Like first one is diffusion. So when we are dealing with fluidized beds, like the solids and the gas is there, in some cases between the solids and the gas, by means of the gas diffusing into the solids, mass transfer would be taking place. That is, we call it diffusion. And the bulk movement of solids from the bed bottom to the bed top, or again falling back, would again ensure that there is certain amount of mass transfer between the particles in the fluid. So by means of that we have convective mass transfer. So next one is the chemical reaction. So fluidized bed is again used in multiple production of various chemicals. So in all those things, the chemical reaction, we need to study the mass transfer phenomena also that is happening inside the bed. So and what are all the aspects we are studying this? We are using fluidized beds to study the mass transfer and the heat transfer phenomena. So in this aspect we are using what to say, diffusion, convection and chemical reaction. So after that, what else we have? It is the heat transfer. So what are all the phenomena that is by means of which heat transfer takes place in the fluidized beds? We have conduction, convection and radiation. Conduction is between the particles and walls, and convection is when gas is transferring the heat to the particles by means of the motion or to the wall, that is by means of convection. And last we have radiation, where the particles, from the particles if heat is transferred to the gas, or from the walls heat is transferred to the gas, we have radiation. So mass transfer takes place by means of three things, like diffusion, convection and radiation, and heat transfer by means of conduction, convection and diffusion, convection and chemical reaction. So the mass transfer, when we are dealing with the mass transfer, there are various things we need to be understood. The first one is the gas solid mass transfer, like the fluid and the solids, between them what is happening, and also the bubble and the cloud. If in general we can identify or separate the fluidized bed into a bubble phase and the emulsion phase. The bubble phase is where there are no solids fraction present, and the emulsion phase is where solids had certain amount of, like similar to that of the fixed bed. So bubble to cloud and cloud emulsion, everything needs to be studied. Bubble is nothing but the where it is, and the cloud is the surrounding region near the bubble. Inside the bubble the solid fraction would not be there, like almost 80% of the bubbles would be occupied without solids. So the cloud to emulsion, emulsion to, I mean bubble to cloud, all these interface mass transfer needs to be studied when we are dealing with the mass transfer phenomena inside the fluidized beds. And there are so many theories available for the same. So that is the thing. So these are the theory summary for the whole concepts behind the fluidized beds. Now we will see what are all the problems that we saw during the course, and we will solve them one by one. So if you have any doubts till now, you can ask. After this we will move to the problems from the week's portion. Like from the important problems throughout the classes have been taken, and that would be used in the a summary. So I guess that's all. Now we will start with the problems for this week. I mean, this is a repetitive problems only, so just to give an idea of what are all the problems that can be asked. So this question 1, it is given cumulative weight of a representative 360 gram sample, and which is having a diameter smaller than dp. So 360 gram cumulative sample weight is given, and whose diameter is given. Like it is 0 gram of particle is in the 50 micrometer range, and between 60 grams to 0 grams it is 75 micrometer, and around 90 grams, 150 minus 60, it is 90 grams of particles are in the fraction of 100 micrometer size. So we need to calculate the mean diameter of the particle of the following size distribution. So we have a particle size distribution given, from which we need to calculate the mean diameter of the particle. So for that, we have given 50 to 75 micrometer of the particles. We have it as average size as 62.5. 50 plus 75 by 2. That is 125 by 2, it is 62.5. Similarly, 175 by 2, it is 87.5. In that fashion, we have calculated the average diameter, and the weight fraction we need to calculate in that particular interval. So it is 60 minus 0 by 360. Similarly, 150 minus 60 by 360, that would give us weight fraction. So it is 0.167, 0.250. Similarly, we calculated the weight fraction of the materials in that particular section. And next we need to find the x by dpi, that is x is the weight fraction and divided by the dpi. So 0.167 by 62.5 gives 0.00267. So similarly, we have calculated the x by dpi, it is 0.01021. I mean, the total of all these gives us 0.01021. So inverse of this gives the average diameter, that is 1 by x by dpi gives 1 by 1 divided by 0.01021, that is giving us 98. So the answer is 98 micrometer. So this is just a sample problem to give you an idea how to calculate the weight fraction diameter of the particle given a size distribution of the particles by having a smaller diameter range, and the cumulative weight of the particle is given. So this is question 2. In question 2, it is asked that calculate the terminal velocity for the sharp irregular sand particles whose density is given as 1.2 into 10 power minus 3 gram per centimeter cube, and viscosity is 1.8 into 10 power minus 4 gram per centimeter per second. dp star is 160 micrometer. Density of solid is 2.60 gram per centimeter cube, and phi s is 0.67. So actually this problem we have seen option A 1, it is 88 centimeter per second. Option B, it is 66 centimeter per second. Option B, it is 66. Option C, it is 77. Option D, it is 55. So let us just take a 5 minutes break. So right now the time is 3:53. So we will meet at 3:58. So yeah, we'll get back. So answer is 88 centimeter per second. I think it is just. So we will see how to solve this. Although we have seen this in the previous few lectures, just for our understanding. So given air density is given as 1.2 into 10 power minus 3 gram per centimeter cube, and viscosity of air is just 1.8 into 10 power minus 4 gram per centimeter per second. And solid properties, diameter of the solid is given as 160 micrometer, density of solid is 2.60 gram per centimeter cube, and sphericity of the solid is given as 0.67. And then to find the terminal velocity, I mean, what do we need to find? We need to find the terminal velocity. What is the asked in the question? Calculate the terminal velocity for a sharp irregular sand particles. The thing to be noted is it is asked for the sharp and irregular sand particles, not a round shaped particles. So for the solids, we have the density of the solids and diameter of the solids, and for gas we have the density and the viscosity. So this is the thing. And after that we have we will see how to solve this. So the first is diameter of the particle is given dp, we know it has 160 micrometer, but we need to find the dimensionless diameter, which is dp into rho g into rho s minus rho g into g by mu square to the whole power of 1 by 3, where it is Hagen number power 1 by 3. So this we are using this to substitute here, and we are getting dp star as 7.28. And next we are finding ut star, which is nothing but 18 by dp star square plus 2.335 minus 1.7445s by dp star power 0.5 whole power of minus 1, or the inverse. When this is the case, 0.5 to 1. 5s is between 0.5 to 1. So we have 5s as 0.67. So this formula is again applicable, and we calculate ut star using this, and we get the value as 1.2938. And we are using u star by using this particular formula, where u star is equal to u into rho g square by mu into rho p minus rho g into g power 1 by 3. So again we calculate it as this u, we are substituting ut star. So u star we are getting it as 87.92 centimeter per second, or 88 centimeters per second. So how are we doing? One more time. We are calculating dp star first, and we are calculating ut star, and then we are substituting that in this particular equation to get the u value, which we are getting as 87.92 centimeter per second, or 88 centimeters per second, which is the right answer. Option A is the right answer. Now okay, 88 per centimeter per second is the right answer. Now we will go to question 3. In question 3, it is asked that air whose density is 1.22 kg per meter cube and dynamic viscosity is 1.9 into 10 power minus 5 pascal second is flowing in a fixed bed of diameter 0.5 meter and height 2.5 meter. So the bed is packed with spherical particles of diameter 10 mm, void fraction is 0.38. Air mass flow rate is 0.5 kg per second. So calculate the pressure drop of the part across the bed of particles. So in this we need to know the pressure drop across the bed of the particles. So it is a very straightforward problem if we look. So air is the fluid whose density and dynamic viscosity is given, and the particles diameter and the bed height is given, and okay, particle diameter and the bed height and the bed diameter is given, void fraction is given, air mass flow rate is given. So we need to calculate the pressure drop. So answer is option A, 0.276 into 10 power 5 Option B 0.286 into 10 power 5. Option C 0.294 into 10 power 5. Option D, it is 0.264 into 10 power 5 Pascal. So this problem we have already solved. So at least write the formula now so that we can use it to solve the problem, because by now we are familiar with all the formula used throughout the course. So I'll give you guys a 1 minute time, if possible solve the problem also, because it is again a simple problem to just calculate the pressure drop across the bed of the particles wherein all the data is given. So answer is 0.264 into 10 power 5 Pascal, which is option D. So what are all the given things? Air is the fluid, so our density of air is given and dynamic viscosity of air is given, which is 1.22 kg per meter cube density and 1.9 into 10 power minus 5 Pascal second. And mass flow rate is given 0.5 kg per second. So fixed bed, its diameter and the bed height is given, and particles, spherical particles, it is mentioned, and diameter is mentioned as 10 mm, and void fraction is 0.38. And what do we need to find? We need to find the pressure drop across the bed, and we are using Ergun's equation. So Ergun's equation is used to calculate the pressure drop inside the back bed, and for that we are using delta P by L is equal to 150 V into mu into 1 minus epsilon square by 5 dP square into epsilon cube plus 1.75 into rho into V square into 1 minus epsilon by 5 dP into epsilon cube. So Reynolds number, it is particles Reynolds number, which is rho V dP by mu. So we need to identify what is V here. So what is V? It is mass flow rate is given. So mass flow rate, it is in kg per second. So mass flow rate divided by density would give us volumetric flow rate, because kg per second by kg per meter cube. That would give us meter cube per second, which is volumetric flow rate. We need to know the velocity. So volumetric flow rate divided by the column area gives us velocity. So we are having mass flow rate as 0.5 and density as 1.22, which is giving us volumetric flow rate, divided by the area of the column, cross-sectional area specifically. So pi r square. So 0.5 is the diameter of the column and 0.25 is the radius of the column. So we are getting the velocity as 2.08 meter per second, and Reynolds number, it is falling under the regime. If we are calculating the Reynolds number, we are getting it as 1.22 into 2.08 into 0.01 divided by 1.9 into 10 power minus 5. This is giving us 1335.58. Because this is coming under the turbulent regime, like we know Newton's regime and Stokes regime, right? This is obviously not in the Stokes regime. Stokes regime would be very low, and this is turbulent regime or the Newton's regime. So we are using only the latter part of the equation. That is, one second. So we are using the Reynolds number, and by using this formula, and we are getting the turbulent regime. So because it is under turbulent regime, we are using this latter part of the equation, which is 1.75 into rho into v square into 1 minus epsilon by 5 into dp into epsilon cube. So this is the formula, simplified version for the turbulent regime or the Newton's regime. So on substituting all the known values in this particular equation, we are getting the pressure drop as 26,091 Pascal or 0.261 into 10 power 5 Pascal. So which is option D, I guess. 0.264 into 10 power 5 Pascal or whatever. I hope this question is clear. If not clear, you can ask. So I mean, you can just look into this slide because it almost covers everything. So yeah, we'll go to question 4. In question 4, it is asked that a shot of gas is injected into a 60 centimeter inner diameter incipiently fluidized bed of 300 micrometer sand, for which UMF is 3 centimeter per second and epsilon MF is 0.5. A 5 centimeter bubble forms. For this bubble bed, find rise velocity UBR, cloud thickness RC minus RB, and volume of wake to volume of bubble FW. So this question also we have seen already. So just take a moment to answer this. At least write down the formula and we will discuss the question in a minute. So solution, diameter of the column is given, I guess. Yeah, diameter of the column is 0.6 meter, that is 60 centimeter, and diameter of the particle is 300 micrometer sand, and UMF is 3 centimeter per second, which is 0.03 meter per second. And diameter of the bubble is 5 centimeter, which is 0.05 meter. I don't know why I haven't given units anywhere, but yeah, it's okay. We need to find UBR, RC minus RB, and volume of wake to volume of bubble. So first it is, we need to find dB by dt, that is diameter of the bubble to the diameter of the column ratio. So it is 0.05 by 0.6, which is 0.0833, so it is less than 0.125. So beyond this it would be slugging bubble, that's why we need to identify the bubbling regime. And for this particular regime, the bubble rise velocity is given by 0.7 into square root of g into dB, which is in centimeter. So we are getting the value as 49.02 centimeter per second. If we substitute all the values in the equation, UBR is equal to 0.7 into square root of G into dB. So we know G as 981, dB as 5, and we are getting UBR as 49.02 centimeter per second. And after that we are getting RC cube by RB cube. We are calculating RC cube by RB cube, which is given by this formula, UBR plus 2 UMF by UBR minus UMF for a 3D bed. So for that we know UBR as 49.02 centimeter per second plus 2 times of UMF. UMF is 3 centimeter per second, and divided by 49.02 minus 3. So on the whole we are getting 1.1956, which is here RC is the radius of the cloud and RB is the radius of the bubble. And RC cube is equal to 1.1956 times RB cube. RB we know it as 5 centimeter, which is RB is 5 by 2 centimeter, and so it is 1.1956 into 2.5 the power cube, and we are getting it as 18.6813, which is RC cube. So RC is the cube root of this 18.6813, and RC we are getting as 2.6533 centimeter per second. I think it is better we write equations. So yeah, RC we are getting 2.6533 centimeter, and cloud thickness, which is nothing but, for example, if you guys remember what is cloud, this is bubble, I mean this is cloud if bubble is like this. So cloud thickness would be this. So we know the bubble dimension as RB, this is RC. So this particular is cloud thickness. So RC minus RB. So RC minus RB, we are getting the answer as 2.6533 minus 2.5, which is 0.1533 centimeter. I don't know why it is. So yeah, I guess you are aware of this. So we are getting RC minus RB as 0.1533 centimeter. And next, what do we need to find? We need to find F fraction of wake. So if this is the bubble and this wake is there, so on the whole we can say it as a circle. So what would be the fraction of wake? So fraction of wake could be volume of wake divided by the volume of bubble. So this is volume of bubble and this is volume of wake. So volume of wake divided by volume of bubble would give the wake fraction. This is volume of bubble, this is volume of wake. And so for example, as we can see here, This is 300 micrometer sand. DP we know 300 micrometer. And we know it as irregular natural sand. So 300 micrometer irregular natural sand. We are getting it around 0.24 or something. Yeah, 0.24. So volume of wake fraction, that is wake fraction FW is 0.24. That's what we were asked to find in this particular question. So first we need to calculate the bubble rise velocity, cloud thickness and volume of wake to the volume of bubble. So this is what we have calculated. Volume of bubble rise velocity, we have used this formula 0.7 into square root of g into dB in centimeter. For this we need to fulfill this particular criteria. dB by dt is less than 0.125. And for RC cube by RV cube, we have used the 3D bed formula UBR plus 2 UMF by UBR minus UMF. And for cloud thickness, thereby we obtain RC minus RB. And volume of wake to volume of bubble, that is wake fraction, we have calculated from this particular chart or figure as 0.24. So it is a simple straightforward question. I hope it is clear. We'll go to next question, question 5. In question 5, it is asked that a fluidized bed reactor of diameter 45 cm working for coal gasification with minimum fluidization velocity of 0.025 meter per second. Average size of coal particles was 272 micrometer, for which minimum voidage is about 0.55. Measured shorter mean bubble size is 10 mm. And for this fluidized bed reactor, calculate the cloud radius in mm. Use G is equal to 9.81 meter per second square. So we need to find the fluid cloud radius in mm. So option 1 it is 3.55 mm. Option B it is 4.55 mm. Option C it is 7.05 mm. Option D it is 6.05 mm. So what are the things that is given? We are given diameter of fluidized bed reactor which is 45 centimeter and minimum fluidization velocity which is 0.025 meter per second, and average coal size is 272 micrometer and minimum voidage is 0.55 and measured sorter mean bubble size is 10 mm and we are given G. So we need to find the cloud radius. So it is somewhat similar to the previous problem. So just try solving it, because however we have solved in the previous things also, previous classes. So I'll give you guys a minute and solve it and then we'll discuss. So yeah, we'll see. It is 6.05 mm, but how do diameter of the bed is given as 45 centimeter and minimum fluidization velocity is given as 0.025 meter per second, and particle diameter is 272 micrometer and epsilon mm minimum voidage is 0.55 and bubble diameter is 10 mm. So first what do? We G is 9.81 meter per second square. So first we find cloud radius, and for that we need to find the UMF by epsilon MF is given as 0.0454, that is 0.025 by 0.55, which is 0.0454 meter per second, that is 45 mm per second. And dB by dbed, that is 10 by 450, it is 0.0222. So in the previous thing itself we saw diameter of the column diameter of the bubble divided by the diameter of the bed. We need to identify which is should be less than 0.125, so that we can use the given formula, else it would fall under the slugging regime. So dB by dbed, it is less than 0.125, and we are using this to find UB. It is 0.71 into G in square root of G into dB. Similarly, same as the last problem, and UB we are using, I'm sorry, it is 981 centimeter per second. And 1 centimeter, actually it should be in centimeter. It should be in centimeter. So it is 0.711 into it would be 31.3, that would give us 22.238 centimeter per second. And when we are converting it into meter per mm per second, we are getting this particular value. And since UB is greater than UMF by epsilon MF, this comes under fast bubble. So we have seen the fast bubble and the slow bubble. If UB is less than UMF by epsilon MF, it is coming under small bubble. So formula for fast bubble, it is RC by RB cube is equal to UB by UMF by epsilon MF plus 2 divided by UB by UMF by epsilon MF minus 1. So we are substituting all the known values in this particular formula, and we are getting 1.7610, which is RC by RB cube. So we know RB, and on substituting that we get RC is equal to 6.038 mm, and diameter of the cloud is 12.076 mm. So yeah, I hope this is clear. Just analyze this particular problem for a minute, because all the formula are given in this slide. If you have any doubts, you ask, or else we'll go to next problem shortly. So we'll go to question 5. In question 6. I hope question 5 is clear. In question 6, it is asked that calculate KBC for the operating conditions. This is from the last week problem. UMF is given as 0.02 meter per second and D is 2.5 into 10 power minus 5 meter square per second. Epsilon MF is 0.52 and the diameter of the bubble is 4 centimeter and G is 9.81 meter per second square. Use Davidson and Harrison expression, 1963 expression. So KBC is 5.14 per second. KBC is option B, it is 15.24 per second. Option C, it is 10.55 per second. Option D, it is 12.14 per second. So we'll just see in question 6 solution. What are the things given? Minimum fluidizing velocity is given as 0.02 meter per second, and diffusivity is given as 2.5 into 10 power minus 5 meter square per second, and epsilon MF is given as 0.52, and diameter of the bubble is given as 4 centimeter, and G is 9.81 meter per second square. We need to find KBC. So the formula for KBC is 4.5 UMF by dB plus 5.85 into d power 1 by 2 G power 1 by 4 divided by dB power 5 by 4. So this is the Davidson and Harrison 1963 expression. So we substitute all the unknowns in this particular equation and we are getting KBC as 5.14 per second. And that's it. I hope this is clear. This is a very simple straightforward problem where we are asked to calculate the mass transfer coefficient between the bubble and the cloud. So for that we are using the Davidson and Harrison 1963 expression. KBC is between bubble and the cloud. So it is 4.5 into UMF. UMF is the minimum fluidization velocity divided by dB. dB is the diameter of the bubble plus 5.85 into d power 1 by 2 G power 1 by 4 divided by dB power 5 by 4. It is between bubble and the cloud. So we are using this diffusivity and all in this expression. So on substituting all the values in the particular formula, we are getting the value of KBC as 5.14 per second, which is option A. So we'll go to question 7. I think it is the last problem for this session. Okay. We have 7 and 8, 2 more problems. And in question 7, we are asked to find the flux of solids carried out of fluidized bed is given by 200 kg per meter square second. Calculate the slip velocity, where density of solid is given as 3000 kg per meter cube and epsilon SE is given as 0.04. Option A, slip velocity, it is 1.67 meter per second. Option B, it is 3.55 meter per second. Option C, it is 4.50 meter per second. Option D, it is 0.67 meter per second. So what are we asked to find? We are asked to find the slip velocity, wherein we are given flux of solids carried out of the fluidized bed by the gas, which is 200 kg by meter square second, and density of solids is 3000 kg per meter cube, and epsilon SE is 0.04. So answer is 1.67 meter per second. And how are we calculating? We are given flux of solids which is 200 kg per meter square second, and rho S, density of solid, is 3000 kg per meter cube, and epsilon SE, it is 0.04, and we need to find the slip velocity US. So formula is GSE is equal to rho S into epsilon SE into US. So we know epsilon SE, we know rho S, we know GSE, we need to find the US. So US is equal to, that is slip velocity is equal to flux by density of solid into epsilon SE. So solid fraction in the emulsion, I guess. So entrained solid fraction, this is entrained flux, solids flux. SE is entrained solids flux, entrained solids fraction. So we are using this to obtain slip velocity. Slip velocity is nothing but entrained solids flux divided by density of solids into entrained solids fraction. So 200 divided by 3000 into 0.04, that is giving us 1 by 0.6, that is 1.6667 meter per second. So that was option A, 1.67 meter per second. I hope it is clear. This is a very straightforward problem wherein we are asked to find the slip velocity given the solids flux in the entrained solids flux, entrained solids fraction and density of solids. So on substituting all this, we are able to get the slip velocity. I hope it is clear. Just take a minute and we will go to the last problem of this session. So we'll go to question 8. In question 8, it is given that the superficial velocity of a gas at 0.05 meter per second is passing through a fixed bed of particle size 3.5 mm. Calculate the Nusselt's number of particles, where data is given as density of gas 1.23 kg per meter cube and viscosity of gas it is 1.83 into 10 power minus 5 kg per meter second, and Cp, that is heat capacity of gas, it is 993 joules per kg Kelvin, and Kg conductivity is 0.0026 watt per meter Kelvin. So this is the problem we saw last class, that is yesterday. So Nusselt's number, particle Nusselt's number we need to calculate. Option A it is 4.89, option B it is 2.56, option C it is 10.86, option D it is 7.86. So I hope you remember. So we'll quickly go through this. Option D is the right answer, which is 7.86. So first, given data, we are given density of gas, viscosity of gas, heat capacity of gas, conductivity, velocity and diameter of the particles. So formula for calculating Nusselt's number is, it is similar to the Sherwood number. Sherwood number is for mass transfer, Nusselt's number is for heat transfer. Whereas in Sherwood number we are using Schmidt number. In in Nusselt's number we are using Prandtl number. That is the only difference. So Nusselt's number is equal to 2 plus 1.8 into Reynolds number power 0.5, Prandtl number power 0.33. So Reynolds number is equal to, this is particle Reynolds number, so rho v dp by mu. So we know rho is 1.23 kg per meter cube and v is 0.057 and dp is 3.5 into 10 power minus 3 divided by 1.83 into 10 power minus 5, which is giving us 13.4090. And Prandtl number, it is given by Cp mu by K. So Cp 993, mu 1.83 into 10 power minus 5 divided by 0.026, which is again giving us 0.6989. So Nusselt's number is 2 plus 1.8 into Reynolds number power 0.5, Prandtl number power 0.33. So on substituting all the known values in the above formula is giving us 7.86, which is, I guess it is option D. Option D, 7.86 is the right answer. Just look at this formula for a minute. If you have any doubts, you ask. So yeah, I guess that's it. I don't know why this font alone is a different one. It's okay. So that's it for today. Um, I'm really thankful for everyone who has attended the session and found it useful. So I guess there is a lot of improvement from my side as well. By having more one-on-one interaction with you people, which I missed out completely in this session, which I completely understand. So this is fault on my side, which I would be improving in the further lectures, that I can promise, because it was, I didn't start, so it was kind of a difficult. So which would be rectified in the further classes, like if ever I take in the future. So I mean I'll be taking for sure in the future. So in those sessions I promise I will be rectifying it. So apart from that, if you have any feedbacks, you can always give it to me. And that is the end of the problem solving sessions for this course, Fluidization Engineering. So I guess it was quite useful because we have seen, almost covered all the important things that we need to be knowing. Just give me a minute. I'll just see if I have left out any important things to be said. So in the meantime, if you have any doubts, you can always ask. So in today's class, I didn't cover about the fast bubbles and slow bubbles and all. To give you guys a one-liner, fast bubble is the one which moves relatively fast. Sorry, fluid moves down relative to the bubble. The bubble would be moving forward and the fluid would be moving down. For the slow bubbles, it is the vice versa, where small bubbles and larger particles would be dealing with that, and slow bubbles would be moving slow and fluid would be moving up. Fluid moves up relative to the bubbles, it is known as slow bubble. Fluid moves down relative to the bubbles, it is known as fast bubble. Slow bubble is observed in the regions with larger particles and smaller bubbles. And apart from that, what have we missed? Slugging formation, we have four categories of slug formation, actually sorry, three categories. The first one is round slugs, and once the round slugs grow in size, we have flat nose slugs that we have seen. And the first one is round nose slugs, and the second one is wall slugs, wherein it attaches with the wall, which is known as wall slugs. And third is flat nose slugs, wherein it almost reaches the diameter of the column. And there are so many models for slugging and all, which you people need to identify and study for the exams. And Cooney and Lawrence's freeboard entrainment model we haven't seen, although we have seen the picture. In that there are three distinct phases. So one is the one which is moving upward, it is gas stream plus the dispersed solids. Another one is the, we have seen two agglomerates, if you people remember. The first agglomerate is coming from the fines coming from the bed, which is moving on top, and the third one is the agglomerates plus a thin layer of particle solids which is moving down. So we have one distinct phase which is moving along with the gas phase, dispersed phase moving along with the gas stream. That is one phase. Two phases are agglomerate phases. The first phase of the agglomerate phase, which is coming from the bed to the top, that is the fines moving from bed to top, is moving upward agglomerate, and moving downward agglomerate is the particles plus thin layer of particles. So that is one major assumption when we are dealing with the Cooney and Lawrence-Field's entrainment model. And mostly we have covered almost all the things. So one more thing which I didn't explain properly in today's class is the distributor design. So give me a moment. So first one is the perforated or multi-orifice opening. So the first is this perforated plate sandwiching a metal screen. So we have perforated plates which is sandwiching a metal screen. I think I said the reverse of that. That is metal screen sandwiching a perforated plate. It is not the case. Two perforated plates sandwiching a metal screen in this. Two perforated plates sandwiching a metal screen, and staggered grid where there is no screen. When large amount of solids are also entering, we use this. And there is lack of rigidity in this. Possibility of gas leakage is there. And we are using this dished perforated plate when it can be used without a support for heavy loads, because channeling occurs at the center. So more orifice near the perimeter and few orifice at the center. More orifice here and few orifice at the center is preferred. 2D perforated plate, it is very limited in use. And next, it is 1 mm to 2 mm to 50 mm in size. The openings can be present. And next is the tubes and caps, which is used for the high temperature or high reactive cases. So here the orifice is there and pressure tapping can be used. So this is the frequently used bubble cap tubes and prevents solids from falling back into the distributors. And pipe grids are sparges and internals, which improves the gas solids contact as the bubble breakup happens, as they break up the growing bubbles. So this is prevents solids logging when gas prevents solids logging. So yeah, that's it. I think that's all. Um, Here we can see so many bubble formation, single orifice. Here the velocity would be UMF. Here the velocity would be UOR. Orifice velocity would be high. Other regions it would be a minimum fluidized condition would be maintained here in these zones. And this is perforated plates. Here the jet formation would be there. And nozzle, they can, the jet actually can cause large disturbance and cause better mixing of particles than ordinary perforated plates. So jet formation can be preferred in that case where better mixing is preferred. Agitated distributors can also be used when we are dealing with the fine solids. So that is for the distributors. I thought I didn't give you a good idea right now. So just for that I gave a little more introduction. So if you have any doubts you can ask now, or else we can, I think this is the end. So I thank everyone for attending the sessions. So since this is a summary, we have just seen what all the things we have covered in the previous classes together with the problems taken from the previous class itself, just to give an understanding. So I wish you all the best in your future career, whatever wherever you are. And also, if for those people who are appearing for the exam, you can surely do it very well. Just think and analyze different options, so it would give us, if you can't pick one option, you can eliminate options also. By eliminating also you can arrive at the answer, so it can be very helpful. uh, you can do the exam very well. So just be confident, you know all the answers to the problems. So just in that moment you need to recollect it. So be calm while appearing for the exam. You can do it. So it is just a small exam, so surely you can do it. Oh, you have it is just similar to the semester exams which you appear in your colleges if you are students, or you would be appearing for so many other things on a daily basis if you are other than students. So it is just a piece of cake for you guys, so you can definitely do well. uh, yeah, I wish you all the best and I thank everyone for attending the classes, and we'll meet again in some other course in the near future. Thank you guys, thank you.